Welcome to The Explainer. In just about any production process, I'm talking everything from baking cookies to building microchips, there's a hidden story buried in the data. Today, we're going to learn how to read that story using a really powerful tool, the X bar and R chart. We'll see how these simple charts can act as an early warning system, telling you if your process is stable or if it's secretly spiraling into chaos.
And this really is the big question, isn't it? At the heart of quality control, this is what everyone wants to know. It doesn't matter if you're making cars, processing insurance claims, or even writing code. You have to know if your process is predictable. Because let's be honest, without predictability, you can't have quality.
Okay, so here's our game plan. First up, we'll talk about why predictability is just so darn important. Then we'll meet our diagnostic tools for the day. After that, we'll get our hands on some raw data and calculate the boundaries of what's considered normal. And finally, we'll plot the results and deliver the final verdict on our process's health. Let's dive in.
All right, first things first, let's really nail down this core idea. Why are we so obsessed with knowing if a process is stable and predictable? What's the big deal? Well, it's actually pretty simple. If you can't predict the outcome of your process, you have zero control over its quality. You just end up with defects, a ton of rework, and all kinds of wasted time and materials. A stable process, on the other hand, that's a consistent one. That's the goal. So, how do we actually diagnose the health of a process? I mean, we can't just look at it and guess, right? We need a tool that gives us a clear, data-driven picture of what's really going on. And that's exactly where control charts come in. The best way to think about them is like a heartbeat monitor for your production line. They track performance over time, showing you the normal, healthy rhythm, and more importantly, flagging any dangerous blips or irregularities. And these two charts, they work as a team, a dynamic duo. The X-bar chart tracks the average, and it's basically asking, hey, is our process centered on the target we're aiming for? At the same time, the R chart is tracking the range, or the variation, and it's asking, okay, is the process consistent, or are our results all over the place? You absolutely need both to get the full story.
All right, enough theory. Let's get our hands dirty and look at the actual data we'll be using for our diagnosis. Think of these raw numbers as the symptoms of our process.
So what are we looking at here? We've got 25 samples, or subgroups. For each one, we took 4 different measurements. Now, the 2 columns that we really care about are the average, that's our X-bar, and the range, which is just the difference between the highest and lowest value in that sample. Right now, this is just a bunch of numbers on a page. Our job is to turn it into a picture that tells us a story. Okay, this next part is absolutely crucial. We're going to build the framework for our diagnosis. We can't just eyeball it and guess what's good or bad. We need to use the data itself to calculate the natural boundaries of what a stable, in-control process should look like. And it's actually a pretty straightforward 4-step process to define what's normal for this specific data. First, we'll find the average of all our sample averages. Then, we'll do the same thing for the ranges. Once we have those 2 magic numbers, we can calculate the official upper and lower control limits for our chart. Let's do it. First up, we take all 25 of those sample averages from our table and we average them. The result is what we call the grand average, or X double bar, and that number is 40.24. This becomes the target, the absolute center line for our entire control chart. It's our bullseye. Next, we do the exact same thing, but for the range column. The average of all 25 ranges comes out to 8.56. This number, called R bar, is super important. It represents the average expected amount of spread, or variation, we should see when our process is behaving normally. Now, we take our averages and we use a standard formula to calculate the upper control limit, or UCL. Think of this as the ceiling. For our data, that ceiling is 46.48. Any point that goes above this line is a major warning sign. And using a similar formula, we calculate the floor, the lower control limit, or LCL. For this process, that limit is 34.00. Anything that drops below this is another big red flag. Okay, the moment of truth. We have our boundaries, the stage is set. It's time to actually plot our data points and do a visual health check. This is where the story really comes to life. So here's our playing field. We've got our center line, our target right at 40.24, and then we have our upper and lower limits, which create this zone of normal expected variation.
Now, let's take our 25 data points and see where they land. As long as they stay between the lines, we're golden. The process is stable.
And when we plot our 25 averages, we see something pretty interesting. Most of the points, they're behaving themselves, just floating nicely between the lines. But we've got a couple of troublemakers. Look at subgroup 16. It's landing exactly on the lower limit. And then there's subgroup 20. Whoa, it has shot way above the upper limit. These are the red flags we've been looking for. Those 2 points, there are signals. They are the scary blips on the heartbeat monitor. So, what's the final diagnosis for our process? What is this chart screaming at us?
So after all that work, after all that analysis, what's the call? Is this process stable, predictable, in control, or is it not?
The chart gives us a clear, direct, no-nonsense answer. This process is unstable. It is not in a state of statistical control, period. And here's why that's so important. Any point that touches or breaks through those control limits is the chart telling you that something unusual happened. This isn't just the normal random noise you'd expect. It's a signal of a special cause, a specific, findable reason why the process went completely off the rails at that moment. And that unpredictability means you have to take action. And that right there is the true power of this tool. The chart didn't fix the machine. It didn't retrain an employee. What it didn't do was sound a very loud, very specific alarm. It gave the investigators a massive clue, pointing them to the exact moments in time, subgroups 16 and 20, when things went wrong. It's not the cure, it's the diagnosis. And it leaves us with the real question. What on earth happened at those exact moments? The chart tells you where to look, but the real investigation starts now.